Good day, everyone. All right, so we are at the last question for 22-23 paper, and this question is going to be about radioactivity. Okay, so specifically radioactive decay. All right, so just to remind you, when you have a radioactive decay, you will have e to the e to the power of negative lambda t. Now, the front values might be different depending on what you're looking for, which I will show you in a minute, right? Okay, so let's look at the question at hand. The half-life of a radioisotope sample is 3 days. So I'll have half-life is 3 days. Okay, if the initial activity of the sample, so initial activity of the sample is 6.5 times 10 power of 3 becquerel, determine the activity of the sample after 4 days. So I'm looking for activity at t equals to 4 days. Now for the first part, should be able to maintain everything in just days. Okay, so what I'll have is that this activity after 4 days is simply going to be a naught, which is the initial activity, times e to the power of negative lambda. T is 4. I need to look for lambda. Lambda can be related to the half-life by just log 2. So it should look something like that. So now I'll have lambda equals to log 2 over 3. And this would give me a value of 0.231, and the units is per day. Okay, per day. So now I can just substitute it into the equation that we have. T equals to 4 days, right? I'll have A naught to be 6.5 times 10 power of 3. I have e to the power of negative 0.231 times 4. So the activity after 4 days, so let's see, after 4 days is simply going to be 2.58 times 10 to the power of 3 becquerel. So that is the answer for B1. Okay, good. So now we want to look at the second question. Let's just draw lines here. Okay, so the second question, this is the first question, and I want to do the second question. The second question asks for an initial number of radioactive decay. Now, another equation for lambda is actually the initial activity divided by the initial number of radioactive nuclei. Okay, so the problem now is that this lambda must be per second. All right, that's the main problem. It has to be per second, whereas what we have here is per day. So we'll have to convert that. Okay, so let me just show you how to do a simple conversion. If I have 1 day, that means I will have 24 hours times 60 minutes times 60 seconds, right? That is true. 24 hours of 60 minutes of 60 seconds each. Okay. Now, what I have instead is 0.231 day. Okay, I have 0.231 per day. If I just divide it 1 over 1 day, which is equals to 1 per day, what I'll have is 1 over 24 times 60 times 60 per second. Okay, so what I need to do now is just multiply it by 0.231. Okay, so then I'll have 0.231 per day is equals to 0.231 24 times 60 times 60 per second. That's what I'll have. And that is the value of my lambda. Okay? That is the value of my lambda. Now, if I were to rearrange the equation that we had, what I'll find is I'll have n naught equals to a naught over lambda. My a naught is just 6.5 times 10 power of 3, but 1 over lambda is 24 times 60 times 60 over 0.231. That would tell me that the initial number of particles that I have is actually 2.43 times 10 power of 9 nuclei. Okay? And that is the final answer for 8b2. So bear in mind that when you use this particular equation, so the equation that relates between number of particles and activity, this must be seconds. This must be in seconds. Okay? Alright, that is all for this video. Thank you very much.